this video, I'm going to explain to you the science of head pressure. That is, the pressure a depth of liquid creates. To make sure you fully understand the concept, I'll take it back to basics by discussing force and pressure with some simple examples, so you can not only calculate head pressures, but understand exactly what is happening. In engineering and physics, you might see head pressure measurements written as inches water gauge, millimeters of mercury, and other height of liquid units. To understand head pressure, we first need an understanding of regular pressure. Pressure, such as psi, bar, or in its SI form pascals, is simply defined as a force acting perpendicular to an area. Let us make sure we understand what force is and how objects with mass create downward force due to gravity. Newton's second law states force can be expressed as mass multiplied by acceleration, or F equals ma. So if a mass is accelerating, it will have a force component that can be calculated. Earth has a huge mass of 5.97 times 10 to the 24 kilograms. That is a lot of mass. Mass creates gravity that acts on surrounding objects. The large mass of the Earth creates enough gravity to keep us moving towards its centre. That's why we don't fly off into space. On Earth, the gravity causes objects to accelerate towards its centre at 9.8 metres per second every second. Let's look at a quick example of calculating force. A cube with 1 kilogram of mass is at rest on a flat surface on Earth. How much force is acting on it due to gravity? As we said before, the calculation for force is equal to mass times acceleration. In the case of our cube, force is equal to mass of 1 kilogram times by acceleration, 9.8 meters per second due to gravity. This gives us 9.8. The unit we use to quantify force is newtons. So we can say that the force created by gravity on a 1 kilogram mass cube is 9.8 newtons. Now we understand what force is and that gravity creates a force on a mass. Let's look at the relationship between force and pressure. As we said before, pressure is equal to a force divided by an area. Going back to our cube with 1 kilogram of mass, if we now give our cube some fixed dimensions and say our cube is 1 metre by 1 metre by 1 metre, we know that the surface in contact with the ground is 1 metre by 1 metre or 1 metre squared. We can now say the pressure it is exerting is 1 kilogram of force per metre squared. As we've just calculated, 1 kilogram of force is equal to 9.8 newtons. So we can define the pressure the 1 kilogram cube is exerting on the ground to be 9.8 newtons per metre squared. Newtons per metre squared can also be called pascals, which is the default unit we measure pressure in. So we can simply define the pressure the cube exerts on the ground as 9.8 pascals. Let's look at an example with psi, or pounds per square inch, and how objects with different masses can exert the same amount of pressure. If we have a 10-pound cuboid with a surface area in contact with the ground of 1 inch squared, we could say the pressure caused by gravity is 10 pounds of force per square inch. If the cuboid has 10 times the mass at 100 pound, but also an area 10 times larger at 10 inches squared, it would still exert the same pressure of 10 psi on the ground supporting it. It all comes down to the height and density of the material over a single area. When looking at psi and other measurements, it's important to realise that the P element isn't just pure mass. The P in psi doesn't stand for lbs, but it stands for lbf, or pounds force. It's the amount of force generated by Earth's gravity for a given mass, as we calculated earlier. Make sure you fully understand these concepts, even if you have to go over it before we move on. Now we understand what the measurement of pressure is, we can dig a little deeper. In our examples, we have been talking about the pressure of solid objects. Liquid and gases also produce a force due to gravity. It's easy to assume that there is no pressure around us on the ground, but this isn't the case. The Earth's atmosphere stretches to over 6,000 miles above sea level, although it's thicker close to the sea and very, very thin at the uppermost heights. The mass of all the gases in the Earth's atmosphere, that are mainly made up of nitrogen and oxygen, give a pressure of 101,000 pascals at sea level due to gravity. This pressure is active on us all at all times. When we talk about pressure measurements on Earth, we frequently use what is called gauge pressure. Gauge pressure uses the Earth's atmospheric pressure at sea level as a reference to zero. The common alternative to gauge pressure is absolute pressure. This excludes the Earth's atmosphere, and the reference point for zero is taken from the pressure of a complete vacuum. Because the atmosphere has a varying density due to gravity and the fact that the gases are compressible, there isn't a linear link between the height of atmosphere and the pressure. Instead, it's more of a curved response, with most of the pressure change happening close to the Earth's surface. Liquids, on the other hand, are less compressible and have less variability of density due to temperature. Also, the heights of liquids we are performing calculations on are much less compared with the atmosphere. The deepest body of liquid being the oceans, with a maximum depth of approximately 7 miles. Because there is less variability, it means we can draw firm, linear relationships between depth and pressure. Have you ever dived underwater in a swimming pool or the sea and felt the pressure acting on your ears? Well, let's look at how we can calculate the pressure of your ears for a given depth. Providing we are swimming in fresh water at approximately 20 degrees, the metric system makes it very easy for us to calculate pressure. Every 10 metres of water is approximately 1 bar. Let's see how this calculation works. 1 bar is 100,000 pascals. Remember, as we said before, a pascal is 1 Newton per metre squared. When we are 10 metres deep, we have the mass of all the water on top of us. That mass is being acted on by gravity to create a downward force. Let's look at how much mass of water is above a 1 metre square area at 10 metres. We can take a column of water 1 metre by 1 metre and 10 metres high and calculate the mass. We know 1 litre has a mass of 1 kilogram. How many litres or kilograms are within our column? A litre of water is 10 centimetres cubed. Using some simple maths, we can divide the dimensions of our column by 10 centimetres and we end up with 10 times 100 or 10,000 kilograms of mass. As we calculated earlier, 1 kilogram of mass gives us 9.8 newtons. So the force of our column of water due to gravity is 10,000 kilograms times by 9.8 newtons, or 98,000 pascals, which is around 1 bar. Luckily, it's a simple equation to remember. Using the calculation we've just completed, we can find the pressure at any depth of water. What if we're not calculating the pressure of a depth of water? In engineering, there are numerous fluids we might need to calculate the pressure of. Luckily, there is only one thing we need to know about the fluid that we are measuring, and that is the density. The density of a fluid determines the mass for a given volume. Densities are given as kilograms per litre. Water has a density of 1 kilogram per litre, as we have been using. Diesel, being lighter than water, has a density of 0.85 kilograms per litre, and liquid mercury has a density of 13.5 kilograms per litre. If we know the density of the liquid, we can simply calculate the pressure as if it were water and then adjust for density. Let's look at our 10 metre pool example, but instead of water, use diesel. Given that 10 metres of water is approximately 1 bar of pressure and the density of diesel is 0.85 kilograms per litre, we can simply multiply our pressure for water by the density of diesel. So 10 metres of water is equal to 1 bar of pressure. 10 metres of diesel is equal to 1 bar times by 0.85, which is the density. This gives us 0.85 bar. Now we know how to convert between a head or column of liquid and pressure. In process engineering, pressure sensors are often used to determine the level of a liquid in vessels, as long as the liquid has a stable density. The calculations we have just used are then used to convert the pressure into a level reading. In pressurized vessels, where pressure instrumentation is being used to determine level, other factors need to be taken into account. I'll go over these in a specific video. If you are interested in this or other engineering topics, then make sure you subscribe for my future videos.